Hello viewers, welcome to add-on. In this question, we are asked when aliasing takes place. Sampling signals less than Nyquist rate, sampling signals equal to Nyquist rate, sampling signals more than Nyquist rate, sampling signals at a rate which is twice of the Nyquist rate. So let us analyze the problem. So sampling is the process of conversion of a continuous time signal into a discrete time signal. So continuous time signal means that this is a continuous time signal, that this signal is defined for all the values of t, right? Because at this point it has a particular value, at this point it has a particular value, at this point it has a particular value. So continuous time signals are defined for each and every single values of time. And for discrete time signals, this is a discrete time signal. Okay. So these are only defined for discrete intervals of time, because in this particular interval we are getting a particular value, and again after this interval we are getting a particular value, and in the middle of this we are not getting any values. Okay, so with the help of sampling we just convert the continuous time signal into discrete time signal. Now the main thing in sampling is the Nyquist rate or the Nyquist theorem. The Nyquist theorem states that any band limited signal, band limited means suppose this signal this is defined, right? This is defined because it is defined up to a particular value which is up to this. Let us consider it is defined from 0 to 2 pi. But if we consider this signal which is increasing, so this signal suppose it has a value of 1 here. So this signal has a value of 1 for all the intervals of time. Okay, from t is equal to 0, if I say, if this is the time axis, so if this is 0, so from t is equal to 0 up to t is equal to infinite, this signal has a particular value. So this is not band limited. So the Nyquist theorem state that any band limited signal which is band limited to fm, fm is the frequency of the signal. Okay, because this signal is a particular frequency, right? So this is a sinusoidal signal, we can represent it by sine of 2 pi fmt. Okay, this 2 pi fm, this is the angular frequency, we can also represent it by omega of m. Okay, so this is the basic representation of a sinusoidal signal. So the Nyquist rate state that any signal which is band limited to fm can be reconstructed from its samples if sampling rate, we represent sampling rate, is greater than equal to 2 of fm. Okay, right, fs is greater than equal to 2 of fm. Fs is the sampling rate and fm is the frequency of the message signal or the input signal we are giving here. In this case this is the sinusoidal signal and fs is the sampling rate. Okay, so there are particular three scenarios when fs is greater than 2 of m, when fs is equal to 2 fm, and fs is less than 2 fm. These are the three scenarios. So we can understand it by basic. Suppose this is a signal, right? If we take, if the sampling rate is greater than twice of fm, it is the oversampling. Oversampling means we are taking many number of samples. Suppose in this scenario we are taking this number of samples, this lines all are samples. So if this all are the samples, okay, the samples, let us say this is the one sample, this is another sample, this is another sample, this is another sample, like this. Okay, so if you just see, we can easily represent it. If we take more number of samples, we can easily reconstruct the signal from the discrete time signal. Okay, so this is the case of oversampling. So in this case our reconstruction of signal takes place. Now the second case is fs is equal to 2 fm. This is the critical sampling, because at this sampling rate we are taking the exact number of the samples which is required to reconstruct the signal. Suppose this is a sample, this is a sample, this is a sample, this is a sample, and this is a sample. So this is the exact number of samples which is required to reconstruct the signal. But if we take fs less than 2 fm, then what will happen? If fs less than 2 fm, suppose is fs less than 2 fm, so then we are taking less number of samples, like this. So then what will happen? We can't reconstruct the signal. Okay, we can't reconstruct the signal. We can also understand it by spectrum analysis. Like, when suppose this is a spectrum, this is the frequency in the x-axis and this is the magnitude in the y-axis. This is the magnitude in the y-axis and this is the spectrum of a signal. Okay, this is the spectrum of a signal when it is perfectly sampled at a sample rate. Okay, this is the spectrum when fs is greater than equal to 2 of fm. So during this time, this we can see these are all just the copies of this. Okay, this is a particular we can say this is a particular spectra and these are all the just the copies. So we can easily reconstruct it by taking this particular instant. But the thing arises when it is undersampled, which is fs less than 2 fm, the copies overlap with each other. Okay, overlap with each other. Suppose if we pass it through a low pass filter, we will be getting uh, this kind of thing. We will be getting this kind of thing. This is our required spectrum. But during aliasing, as we can see, overlapping occurs here, right? Overlapping occurs here. So if we pass this portion to a low pass filter, we will be getting a kind of this kind of spectrum, which is our which is not our required spectrum. So this is the aliasing phenomenon, and this only occurs when fs is less than 2 fm, where fs is the sampling rate and fm is the what we can say, fm is the message signal frequency. Okay, or we can say it as an Nyquist rate. Okay, so in this question, aliasing occurs when the sampling signal is less than the Nyquist rate. Okay, which is our option number A. Thank you.